Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the PVT behavior of gas mixture. An ideal gas is defined as a gas whose molecules are spaced far apart so that the behavior of a molecule is not influenced by the presence of other molecules, a situation encountered at low density. We also mentioned that real gases approximate this behavior closely when they are at a low pressure or high temperature relative to their critical point values. When two or more ideal gases are mixed, the behavior of a molecule normally is not influenced by the presence of other similar or dissimilar molecules, and therefore a non-reacting mixture of ideal gases also behaves as an ideal gas. Air, for example, is conveniently treated as an ideal gas in the range where nitrogen and oxygen behave as ideal gases. When a gas mixture consists of real gases, however, the prediction of the PVT behavior of the mixture becomes rather involved. The prediction of the PVT behavior of gas mixtures is usually based on two models. The first model is the Dalton's law of additive pressures. It states as the pressure of a gas mixture is equal to the sum of the pressures each gas would exert if it existed alone at the mixture temperature and volume. The second model is the Amenget's law of additive volumes. It states as the volume of a gas mixture is equal to the sum of the volumes each gas would occupy if it existed alone at the mixture temperature and pressure. In these relations, Pi is called the component pressure and Vi is called the component volume. Note that Vi is the volume a component would occupy if it existed alone at T max and P max, not the actual volume occupied by the component in the mixture. In a vessel that holds a gas mixture, each component fills the entire volume of the vessel. Therefore, the volume of each component is equal to the volume of the vessel. Also, the ratio is called the pressure fraction, and the ratio is called the volume fraction of component I. Dalton's and Amenget's law hold exactly for ideal gas mixtures, but only approximately for real gas mixtures. This is due to intermolecular forces that may be significant for real gases at high densities. For ideal gases, these two laws are identical and give identical results. The volume a component would occupy If it existed alone and the mixture T and P is called the component volume. Now, let's talk about the ideal gas mixtures. For ideal gases, Pi and Vi can be related to Xi by using the ideal gas relation for both the components and the gas mixture. This equation is only valid for ideal gas mixtures as it is derived by assuming ideal gas behavior for the gas mixture and each of its components. The quantity is called the partial pressure, and the quantity is called the partial volume. Note that for an ideal gas mixture, the mole fraction, the pressure fraction, and the volume fraction of a component are identical. The composition of an ideal gas mixture is frequently determined by a volumetric analysis. Now, let's talk about the real gas mixtures. Dalton's law of additive pressures and Amenget's law of additive volumes can also be used for real gases, often with reasonable accuracy. This time, however, the component pressure or component volumes should be evaluated from relations that take into account the deviation of each component from real gas behavior. One way of doing that is to use more exact equations of state instead of the ideal gas equation of state. Another way is to use the compressibility factor S. The compressibility factor is determined either at T max and V max or at T mix and P mix for each individual gas. Using Dalton's law gives more accurate results. Another approach for predicting the PVT behavior of a gas mixture is to treat the gas mixture as a pseudo-pure substance. One such method proposed by W.B.K. in 1936 and called case rule involves the use of a pseudo-critical pressure and pseudo-critical temperature for the mixture, defined in terms of the critical pressures and temperatures of the mixture components S. The compressibility factor of the mixture is then easily determined by using these pseudo-critical properties. The result obtained by using case rule is accurate to within about 10% over a wide range of temperatures and pressures, which is acceptable for most engineering purposes. Another way of treating a gas mixture as a pseudo-pure substance is to use a more accurate equation of state, such as the van der Waals, Beatty-Bridgman, or Benedict-Webb-Rubin equations for the mixture, and to determine the constant coefficients in terms of the coefficients of the components. In the van der Waals equation, for example, the two constants for the mixture are determined from. Okay, that's all for this task. Thank you very much, and see you next time. 好。